Hi everyone! In our last lecture, we made a lot of progress in investigating integrals which lead to inverse trigonometric functions, whether they be arcsine, arctangent, or arcsecant type integrals. We started off by taking the basic differentiation facts about those inverse trig functions, and we didn't just turn them around into integration formulas. We also looked to see, well, because each of the resulting integrals has a constant term of 1 in the denominator, we asked the question, what if we replaced 1 with any constant term, and we used a u substitution to answer that question, which gave us more generally useful integration formulas. Finally, we turn our attention to the situation where the quadratic expression that again pops up in each of those inverse trig type integrals, what if that included a linear term? Because from the derivative, it doesn't. It includes a quadratic term and a constant term, but not a linear term. And so if a linear term is present, we may still be able to use those inverse trigonometric integrals, but first we have to complete the square. And so we finished off that last lecture by starting an example, which we didn't have time to complete, where that was exactly our approach. So we're trying to integrate the function 1 over x minus 1 times the square root of x squared minus 2x minus 4. So that has a linear term, the minus 2x. And so what we've already done is we've completed the square. We've shown that x squared minus 2x minus 4 can be rewritten as x minus 1 all squared minus 5. And so therefore the entire integral can be rewritten as the integral of 1 over x minus 1 times the square root of x minus 1 all squared minus 5. All right, well, now we've got the integral in a form where we can evaluate it, but we still have to actually do the evaluation. And so now, because we don't just have an x squared here in the square root, we've got some other expression squared. What we talked about a little bit in the last lecture is that that's likely going to set itself up for a u substitution. So in particular here, we're going to let u equal x minus 1, which is nice because x minus 1 also shows up outside the square root. So we're going to have a u squared in here, and this will just become a u. And du is just going to be, well, the derivative of x is 1, so du is simply dx. So this is one of those nice cases that we don't see very often where we actually can just replace the original differential with the new differential. We don't need to bring any other expressions into play with it. So then, our integral is going to become, well, instead of what we originally had, now we've replaced all of that with, let's see, the 1 stays in the numerator. And then, like I said, that x minus 1 outside the square root, that's equal to u. And the stuff inside the square root becomes u squared minus 5. And then dx and du are the same thing in this case. Right, so that is now in the form of an arcsecant type integral. Because we know in general that if we've got the integral of 1 over x times the square root of x squared minus k squared, that would give us 1 over k times the arcsecant of x over k. Here we've got u's instead of x's, but we know that's not a big deal. But we do have to be careful about that constant, because especially when we don't get a perfect square there, it's very easy to think, oh, well, the constant, the k in this case is 5. But no, remember, 5 in this case is k squared. So yes, this is an arcsecant type integral, but it's an arcsecant type integral where k squared is 5, which means k is the square root of 5. So therefore, this is going to give us 1 over root 5 times the arcsecant of u divided by the square root of 5 plus c. And then we don't like to leave square roots of constants in denominators, so we should rationalize that. 1 over root 5, if we multiply that by root 5 over root 5, would be the square root of 5 divided by 5. So that's what we'll have outside here. And while we're doing that, we might as well also substitute back in for u. U, remember, is x minus 1. So we're going to have root 5 over 5 times the arcsecant of root 5 over 5 times x minus 1 plus c. So there's how to evaluate that integral. So yes, it's an arcsecant type integral, but it takes the combination of completing the square and u substitution. And this is something now that's becoming kind of a recurring theme as we've been making our way through increasingly complicated integrals. So that often it's not just one approach that is going to work. It's a combination of approaches. So far, we've often combined some sort of algebraic or trigonometric manipulation with our integration technique, and that's because basically we've only got one. We've got u substitution. But the deeper we go into this course, we'll also see cases where we're going to have to combine 2 or potentially more integration techniques as we get introduced to more and more methods. So that's something to keep an eye on as we go along in Math 1001. Now, I mentioned in the last lecture that the strategy I outlined there for completing the square, that assumes that the coefficient of x squared is equal to 1. So it doesn't really have a coefficient for all intents and purposes. When that coefficient of x squared is something other than 1, I've seen all kinds of different approaches to how to handle that, some of them kind of convoluted. But the reality is that the simplest approach, the one that I find works by far the best and leads to the fewest mistakes, is simply to get rid of that coefficient. And we can do that by factoring it out. So to complete the square, for an expression of the form, so now we're talking about ax squared plus bx plus c, where a in this case, we want that to be a constant other than 1. We first factor that constant a out of the entire trinomial. So in other words, then we'll have a outside of a quadratic expression that does have 1 as its leading coefficient, as the coefficient of x squared. Then we can apply the exact same method for completing the square that I described in the last lecture, and then we can just multiply a back in. So we complete the square for the remaining quadratic expression, the remaining trinomial, and multiply a back in once we've done that. You'll see other methods where the thing that you add into the brackets and subtract outside the brackets, that you try to account for the value of a and stuff like that, it's unnecessary. If you've seen that before, you're comfortable with it, you know how it works, then I'm not going to say you can't use it, because you'll certainly see it in lots of different reference books. But I really think that what I've described here is the way to go, especially if, as I expect is the case for many of you, completing the square is either new to you or might as well be new because it's so long since you talked about it in the first place. Let's do an example like this in the next video.